we'll discuss the relative motion between two objects, or two particles, using translating axes. Realize that relative motion between two objects becomes important, as in the case of these jet planes flying in close formation, or here, where a collision is to be avoided. So in this lesson, we'll study the relative motion of one object relative to another when the observer is moving, as in the case of these two people moving on different escalators. Now, in order to develop the method for measuring the relative motion of one particle with respect to another, we'll consider these two particles A and B, which move along separate paths. The fixed xy coordinate system that you see here is used to measure the absolute position of each particle. Another set of coordinates, the translating x' y' axes, are attached to the particle at A and moves with it. But keep in mind that these axes don't rotate. And so the absolute position of A with respect to the fixed reference is defined by the position vector r of A. And a relative position vector extending from A to B is called r of B with respect to A. Finally, if we want to find the final position of B, that is the absolute position r of B, we simply do it by vector addition. In other words, r of B is equal to r of A plus r of B with respect to A. And by the way, this formula is relatively easy to memorize if you realize that this A, as a subscript, will cancel with this one, and therefore we have the B on this side as well as on this side. And now that we've established a relationship between the position vectors, we can now take the time derivative of this equation and find our velocity relationship. Realize that these vectors don't change their direction because the translating axes from which you measure r of B with respect to A doesn't change the directions of the components of this vector. Only the magnitude of the components will change. And so the time derivative of this equation will give us our velocity equation. Finally, another time derivative will give us our acceleration equation. Notice that all three equations have essentially the same form. But how do you apply them? Well, let me give you a simple example, say for finding the velocity of B with respect to A. And then in a follow-up video, we'll do more numerical work with these equations. Let's consider this problem then. Here we have the velocity of B given, and we're given the velocity of A. Two cars moving along, and we're asked to find the relative velocity. In other words, the velocity of this car as seen with respect to this one. To solve the problem, we'll first set up an xy coordinate system like this, a fixed system. And of course there'd be a translating system right here at A, parallel to the x and y axes, of course, and moving with car A. But we won't show that. We can now apply our key equation. What I find most efficient is to show each of these terms graphically first, and then resolve it into components. So I'll begin by writing this term. We know its magnitude, which of course is 40, and we know its direction. It goes to the left. We set it equal to v of A, and we know that as well. It's a vector that goes up this way at 50, and its direction is on a 3, 4, 5 slope. Now we don't know the components of this vector, and so what I do here is I show each one in the positive directions. So I write the first one as v of B with respect to A, x, and it goes positive to the right, of course. Then I have my other component. Again, another unknown, of course. V of B with respect to A, and this is in the y direction. And it's positive upward. Now I'll resolve all the terms in the x direction, and we'll write a scalar equation in that direction. So here I have minus 40, and I set that equal to 50 times what? 3/5, right? Here, of course, I have plus v of b with respect to a, and this is in the x direction. And here I have no contribution. You can either add this as a 0, or you can neglect putting it in the equation. Anyway, when I solve this for v of b with respect to ax, I get my answer. It turns out to be minus 70. So I show that with a little arrow like this, or you can include the negative sign if you like. Now let's sum in the y direction. From here I have no contribution. I set that equal to, for here, 50 times 4/5. And that, of course, is positive. Then I have plus, nothing from here. And finally, I have my last term, which, of course, is v of b with respect to a in the y direction. There we go. Now, if I solve this equation, I get the result of v of b with respect to a in the y direction equaling minus 40. In other words, the component goes downward. And now that I know the two components, I can then add them up vectorially, and I can find my velocity of b with respect to a. To do that, of course, I would use Pythagorean's theorem, wouldn't I? The square root of 70 squared plus 40 squared comes out to be 80.6 meters per second. If you want to find the direction of this vector, you could, for example, find the angle right in here, angle theta. How do you get that? Take the arctangent of the opposite side, 40, divided by 70, and you'll find the result. So having given you some idea on how to do these problems, we'll do some more of them numerically in a follow-up lesson. But for now, we'll end this lesson.